Assalamu alaikum. I'm Umar bin Fahim and this is Sayyid Isaac Abdullah. Today we're presenting our comprehensive report on temporal and category-based CPI network analysis for discrete structures.
Our executive summary reveals the power of this analysis. Using discrete mathematical structures and network theory, we identified the most influential cities in Pakistan's pricing ecosystem. This chart shows our key findings. Karachi leads with the highest influence score, followed by Ladkhana and Hyderabad. These three cities are the central hubs driving price patterns across Pakistan.
Our analytical framework transforms raw CPI data into mathematical networks. We analyze spatial relationships between cities, temporal dynamics showing network evolution, and diffusion patterns identifying pricing hubs. The pipeline has five stages: data preparation, network construction using cosine similarity, centrality analysis with four matrices, weighted aggression, and temporal analysis using Hasse diagrams.
The technical implementation starts with data validation. Our input CSV requires city, year, category, product, and price fields. The code cleans data by stripping whitespace, converting types, and handling missing values through product level mean imputations.
We build city product pivot tables for each year category combination, then compute cosine similarity between cities. The formula dot product divided by magnitude product captures directional alignment of price patterns regardless of scale. The network visualization shows a high threshold example at zero point 0.8 for clothing in 2023, revealing only the strongest market connections.
The code construct weighted undirected graphs where nodes as cities and edges exist when similarity exceeds or thresholds. We analyze at three thresholds: zero point 0.6, zero point 0.7, and zero point 0.8 for sensitivity analysis.
This is where discrete structures shine. We compute four centrality measures. Degree centrality measures direct connectivity. High degree means a widespread market integration. Closeness centrality means average distance to all nodes. High closeness indicates central positioning. Betweenness centrality counts shortest paths through a city. A high betweenness means bridging importance. Eigenvector centrality measures connections to influential nodes. High eigenvector means elite cluster membership.
The challenge is combining these four measures into one score. We use three weighting schemes. Scheme 1, equal weighting 25% of each matrix as our baseline. Scheme 2, entropy based weighting from information theory. We construct Shannon entropy for each metric. Higher variability gets higher weight. This is completely data driven and automatically downweights the reducting matrices.
Then assign inverse weights based on redundancy. If degree and closeness are highly correlated, both get reduced weight to avoid double counting. This produces more stable rankings.
Within each year, we aggregate category scores using equal weights, producing year level rankings under each scheme. This final visualization shows the multi stage aggregation outcome combining all centrality measures, categories, and years.
For temporal analysis, we use partial orders from discrete structures. We define a relation between years based on edge set inclusion. Year 1 precedes year 2 if all edges in year 1 also exist in year 2. This relation is reflexive, antisymmetric, and transitive, satisfying partial order axioms.
We visualize this with Hesse diagram, showing cover relations, direct precedence with no intermediate year. Upward paths indicate network expansion as edges proceed year over year. Disconnected nodes shows structural change where the network fundamentally reorganized. This reveals whether markets are integrating, fragmenting, or staying stable.
Our systems generate extensive visualization, similarity heat maps. One second. Similarity heat maps use weirdest coloring, yellow for similar pairs, purple for dissimilar, revealing cluster structures. Network graphs use spring layout with edge width proportional to similarity. These comparative visualizations show how food categories have different connectivity than utilities.
Key output files include similarity matrices for verification, edgelist for importing to Gephi, centrality tables with all four measures, integrated rankings for policy decisions, and comprehensive summaries comparing all three schemes. This enables consensus ranking and sensitivity analysis.
High influence cities like Karachi, Larkana, and Hyderabad exhibit three characteristics: spatial centrality in dense network areas, market integration with aligned price patterns, and structural importance as bridges between segments. They're essential to the system's architecture.
Some cities show scheme-sensitive rankings, varying across methods. This dense network for oils and sweeteners show how connectivity patterns affect weighting schemes. High redundancy in centrality measures gets adjusted downwards by correlation-based weighting.
The system is modular and configurable. Users can adjust thresholds, weighting schemes, and years analyzed. Computational complexity uh, f- uh, complication complexity is the formula for N cities, M products, and Y years in C categories.
Applications span three domains for economic policy, identity, inflation, monitoring targets, and optimize subsidy distribution. The top ranked cities are strategic intervention points. Influencing prices there creates a cascading effect. For business, optimize retail expansion and pricing strategies. For research, extend to multi-layer networks and predictive modeling.
We've transformed raw CPI data into actionable insights through rigorous mathematical modeling, combining network theory, information theory, and discrete structures.
The three weighting schemes offer analytical flexibility, while temporal analysis reveals market evolution. This modular framework works for diverse economic datasets. Thank you for your attention.